Hey.
Going.
Oh, not too bad.
Yeah. That's good. How's quantum treating you?
Well, so far it's okay. We're doing we've got a homework that's got a bunch of matrix reviews.
Okay, yeah.
It's been a while.
Yeah. Probably good good stuff to review. How many people are in that class?
I think it's
4?
5 of us.
5? Okay.
Because I know that we have enough, we can 6 in here if we said we want to do it here.
Mm-hmm. Cool.
Morning. Well, not morning, sorry, afternoon.
Set this up before.
Thank you.
More logins, I suppose. Oh, Michael. Hello, Michael. Can you hear us? Think.
Hi.
Yeah. Okay, good.
Dr. Berg is talking to us on that PGL classroom, virtual classroom. Every time you mute or unmute, there's a little, you are now muted. You are now unmuted. And so if you get to the point where you don't want to unmute, so you don't want to answer questions.
The automated voice.
Yes, automated. You can't, that I know of, you can't stop it.
Yeah, no one else hears it though, it's just for you.
Oh, nobody else hears it.
Yeah, it's just for you.
Oh, it's for
your-
yourself.
for your
Oh, I
sake,
see.
yeah.
Oh,
Unless your microphone is fairly.
If only in the case where there's feedback, but from my experience, it's yeah, it is annoying.
yeah. I think it's, I know this from subway trains, like metro trains. Like every time the door opens,
Oh
there's
yeah.
a whole 2 sentences. Stay away from the door.
Mhm.
It's opening. So it's good it's a safety thing I understand, but
Yeah.
after a while it is so monotonous.
Yeah,
That,
yeah.
yeah, I wouldn't say you hate it, but yeah, it's too monotonous.
Mhm.
Okay, so 1, 2, 4, 4. Jordan and Oliver.
Spoke his name, very.
Oh, there you go. Jordan.
Hello.
Very dull hello.
Huh?
Very dull hello. We just mentioned we just mentioned your name, saying that you and Ali are missing, and you just logged in. So we were saying,
As if by magic.
yeah, Jordan was. We're just waiting that you mention him, and then I'm like,
Just don't say his name into the mirror 3 times.
until what? And
It was a
Same.
movie where you said this thing into a mirror, it would manifest itself, and you had to say it 3 times, so don't say his name in a mirror 3 times. Otherwise, you have to buy him dinner.
Nice.
And give him a ride back to home.
That's your wish. Okay. Let's see. I did set it. Let me see if it works. These double digits really don't work actually. I was thinking I was setting the double digits last time. It's just it senses the last one. So first digit is just muted. So I'll find out how it is. They say it is 64 presets.
Oh.
So surely something is there in it because there are only 9 numbers there. So there must be some way to do that. Okay. So oops. Homework due Tuesday. What was the homework? What was it about? I don't remember the homework. 2.
To do with the line,
Yeah, I think
straight
it is
wire.
straight wire. Okay. That
I
doesn't
think I haven't actually looked at it.
Yeah. I think it has to do with the flux probably. I was thinking, what did I ask? Okay. That's homework too. Tuesday. So still available more than 3 weeks or so. Okay. We talked about the magnetic field due to a wire and also the magnetic vector potential due to a wire. So we have been able to calculate that. And when you do electric field, if you were to calculate the electric field due to a point charge, of course you can do the Coulomb's law and get it explicitly calculate. But there's also an easier way when we're working with electric field, and that's Gauss's law. Whenever the symmetry is extremely high, Gauss's law does a good job. And there's a corresponding thing here. What is it called here in magnetic field? What's the Ampere's law? So you can, for simple geometries like a straight wire, you can use the Ampere's law to get it. So I'll very quickly do that. And then we want to get into the circular wire, how we do the circular wire. And we will see that there are complications, or it's not an easy expression for the circular wire. We will then postpone it and do it for a very small circle, like if the observation point is extremely far away from the circle, then it has a very neat, simple result. And then we'll come back and of course do the circular wire in detail. So we'll spend about 2 weeks or so on the circular wire itself. So let's begin by doing the same result that we got for the magnetic field for a straight line using Ampere's law, and see just so that we have a complete story of we are aware of what Ampere's law is. So we want to do Ampere's law. What Ampere's law says is it starts from del cross E is equal to mu naught J, right? So that's your magnetostatic equation. There is also one more equation, and that's del dot B is equal to 0, right? So that's your, and of course, if we want consistency with Maxwell's equation, we want the J also will be divergence. So this is an important relation. J is the source and magnetic field is what it produces. How do we get the Ampere's law? Just integrate this on any area. So let's say there is an area S. So there is a magnetic field. Let's say so this is the surface, and we could have a magnetic field coming out. So that's your magnetic field. That's it. So of course, and that's your surface S. So that's what I'm integrating on. And we have del cross D, no space. A is equal to mu naught is a constant. A with J on the same suffix. That's your B. What I did not say is that this also carries currents, right? We might have some current carrying wire there. I haven't drawn the current carrying wire. So some current that produces this magnetic field. It could be a complicated configuration there. So I'm not drawing that. But what is J dotted with dA equal to? Like, if you were to integrate current over an area, simplest geometry you can think of is if you have a cylinder, right? Let's say that's your S. Let's say so. That's and let's think of current being going in a straight line. So that's current, but then you would say current I, let's say, per unit area is equal to what is current per unit area?
Current density.
Current density, and that's your J. Right? And I then is equal to J, if this was a small area, so that's J dotted with dA. Let's say this is dI. Small element there. And then you integrate this over all the area, and that's the total current I. Oh, am I within that? No. So I is equal to Sj dot dA. But notice there could be current moving outside the surface also. So I should say this is the enclosed current. If there are more currents than that is passing through the surface S, so I should call that enclosed current. That's one fact, but we can also integrate the left-hand side. So the right-hand side seems to have a simple expression, that's I enclosed. Very similar to what we have in the case of Gauss's law, where we talk about charge enclosed, right? Integral there, you integrate over volume, and then you get the charge. It's also important here as to when you say charge and current enclosed, current has a sense of direction, right? It could be coming out of the board or going into the board. Like if you have a surface, there could be a current going onto the right in the sense, or going into the surface. Then which way is positive and which way is negative, right? So that seems to have some confusion there. So I'll come to that in a minute. Before that, let's go back in here. this will decide what's the direction sense in there. What is this equal to? This is Stokes' theorem, correct? Area integral of a curve is equal to a line integral, correct? So this is a line integral, a closed line integral, and that's dl dotted with d. And it's understood that this line integral is the boundary of that surface S. But having said that, it doesn't have to be the boundary of that surface alone. That has a unique boundary, but then that surface itself, you can move it around. Like given a boundary, then I can change the surface. So it's not really necessary to put that S in there. But now, notice, when I did this, there was an area vector. So if I were to have a single wire, let's say, so this is a current I coming out of the board, and that represents current out of the board. And let's say the surface was this, so that's your S. Now, when I say dA dotted with that, that has a direction in the sense, am I talking about the area coming out of the board or going into the board? So that fixes my direction. Let's say that that's dA is coming out of the board, then my J has to be counterclockwise with respect to that direction. Right? So there is a right-handedness in there. So how do you say this? Yeah, so this line integral here is having a sense of direction. So this is equal to, so this is counterclockwise. Did I say that right? So this is a counterclockwise sense for this line integral, because I could have had it in the opposite direction also. And that's decided by dA, and accordingly the current is got using the right hand rule. So you use your fingers to have the direction of this counterclockwise sense, and your thumb is coming out in here. So I said it in many words, but the point here is that there is a right-handedness being used here. Right-handedness is implicit in this in the Stokes theorem. Right? That is it's not a left-handed. That will give you an opposite. Okay, with that, we can actually calculate as an example, simple example, we can calculate the magnetic field due to a single wire, right, which we already did. We know the result, but let's quickly do that. So this is an example. So example is infinitely long or infinitely long wire, right? Straight wire. Okay, and we know the result, of course, but we want to, and what's the result? Let's say this is B is equal to mu naught over 4 pi. It's out of the so B is equal to mu naught over 4 pi times 2 times I over rho. Rho is the radial distance from the axis of representing the wire, and phi hat. Right? This was derived from the scratch, so we do know that that is in the phi hat circular direction. But now let's come to the Ampere's law. So how do we go about doing this? Right. So first there is a wire. Let's put it at the center, and so this is coming out of the board. So that circle means that there is a current I coming out of the board. Let's say there is a there is a Ampere's loop. So this is the Ampere's loop. There we talk about a Gaussian surface, right, in electric field. So this is a Ampere's loop, and we have to calculate the right-hand side for this. And for that, I need to know what is my B to begin with. So let's say DL, it's clear for the loop. It's in the direction of phi. So that's in the direction of phi, and let's say this is your distance rho. So that's your rho, and what am I missing? Rho times d phi, right? Or let me just say dl. Right? Talk about all this. Just phi hat, direction is phi hat, and the length is just dl, and then I'll add up all length. Right? Okay, so my integral then becomes integral. So this is dl phi hat dotted with now magnetic field. So I have to say something about the magnetic field if I want to evaluate that. So that's equal to right hand side is clear, that is mu naught enclosed, so that's mu naught I. So this is where Ampere's law uses symmetry. So now I have to talk something about B. I pretend that I don't know this result for the magnetic field, but I have to say something about the magnetic field so that I know what this is. So first thing you say is that this is an axially symmetric system. Whatever is on this side at this point should be the same as that point, same as it. So the world looks the same if axis is the only point in there. So it can grow. So B magnitude wise, so let's say magnitude of D, that depends only on rho. What else can it? So it cannot depend on phi or Z. So there is no Z dependence. So there's only a rho dependence in there. So I can bring that out, but then the direction of B comes in, right? So let me say D is equal to B of rho times some direction B hat. I don't know what that B hat is. And here I bring that out since it is only a rho dependent quantity, does not depend on phi. It can come out, and this is all on a plane, so there's no Z dependence. So this is B of rho times integral of the L phi dotted with the hat. And that's equal to mu naught times I. Okay. And then you say, what should B hat be? What should be the direction of the magnetic field? Can you have, so to begin with, like of course we know the answer is radial. What's wrong in the following sense for magnetic field? Of course, the magnetic field is like this, right? This is what our magnetic field looks like. Like at each point, it's tangent to a circle, right? That's how magnetic field looks like for a single wire. But what's wrong in this following scenario? That it's like this. Is that clear what I mean? So, for example,
There's a divergence.
that's very correct. Now the point is, one would think that, oh, this is still having the axial symmetry, but if you were to calculate the divergence of B, remember that we have to have divergence of B is equal to 0. Very good answer, because this has a radial component in it. So we know that whatever this is, this will contribute to a source at the center, and we cannot have have a source in there. So this has to have a phi hat, and that has to be a z hat component, z hat also. So how can you argue the z hat direction? How do you argue that this cannot have anything coming out of the z hat direction? Offhand, I don't know. Okay. Quiz. So why can't the magnetic field have a rho hat direction? Moses pointed that out correctly. Why can't it have a z hat component? Right. Quickly try to do satisfy this equation and any other symmetry equation you have, and it should be possible to show that there is no z component to the magnetic field. Is the question clear? Quiz. Why can't we have a z component in it? So based on those arguments, you say that, oh, B hat has to be phi hat. So that's a request. So before you begin Ampere's law, you're already saying that B is equal to some radial dependent times phi hat. Right? That's already inbuilt in there. So that becomes 1, this becomes 2 pi rho, and that immediately gives you B rho is equal to 2 pi times pi times rho equal to mu naught I, and we have mu naught I over 2 pi rho, which is of course the answer as far as the magnitude goes, and the direction anyway we put it in there by symmetry argument. So it comes out reasonably very immediately, and it's just a matter of getting a vector potential, correct? What vector potential gives you this quantity, and we have seen that that's usually a harder thing to calculate, in the sense there's a gauge dependence in there, so we won't be able to capture everything, but we explicitly calculated that in the Lorentz gauge, if you want. Okay. So there's one more example which is nice to do in the case of Ampere's law, and that is the magnetic field due to a solenoid. Right? What is a solenoid? What is a solenoid?
Like a cylinder with current
Yeah,
passing.
cylinder with a coil-like structure for the current. So what is the magnetic field inside a solenoid?
It points in one direction through the axis, the central axis.
And is it higher at the center or closer to the sides?
Well, it should start, once you get to the sides, it should start falling off as, right? So it's
Sides, you
higher
mean?
on the surface.
No, I think so. I think Moses had it. Okay, so let me draw this first of all. So these are wires, right? If this makes sense, right? Stacked on each other. This is the coils of stacks on each other. On one side it's coming out, and the other side is going in. Right? That's going in, and this side is coming out. And you can keep doing this forever. Right? So it's important that this is infinitely long. Right? And then the question is, what is the magnetic field inside? So now that I've given you the direction, what's the magnetic field inside? Is it up or down?
So,
Right, so it's up in here. Right, that's your magnetic field. Let's say that's your z-axis. So B apparently is z hat, right? And then we have to ask, how does it depend on the radius of this coil? So this is a cylinder, right? So let's say that has a radius in there, and you can ask what is the radial dependence in there. And that was my question. is it farther, as you get farther, what does it happen? And I think Moses said that it is independent, sort of constant, right? So it does not depend on the radius. That's remarkable, right? I mean, so anything, when you have a parameter and it doesn't depend on, that means you can exploit that somehow. What will happen if you get really small? It seems like it is small. I mean, it doesn't depend on A. You can really squeeze it to 0 apparently, right? And still your magnetic field will exist, right? Because it does not depend. At least theoretically speaking, you can really make it small and you're still good. So whenever something is outright not dependent on something, that is a nice feature in that. For example, a sphere, right? The same thing with electric field. If you have a positively charged sphere, a conductor, perfect conductor, what's the electric? So this is radius r, right? And let's say this is the observation. What's the electric field at that point? How does it depend on the radius r? So the electric field at this point, what is it?
It's independent of capital R.
It's independent of capital R. That's a point. So that's 1/4 pi epsilon naught. And it is just, I should have put a Q, maybe that was what was confusing. So Q, right? So Q over R square, and it's R hat. No dependence of capital R, which means to say that I can really start squeezing this this radius R and go all the way to actually 0, and still your physics will not change, or at least your equations, Maxwell's equation allows that feature in there. So that feature is in here also, and we'll talk about that sometime, like probably 1 week down the line, where we will try to squeeze this. But as of now, this is independent of A, and so that means that however closer you get, that's perfectly fine. But if this was having a cut, I think that's what probably Jordan was trying to say. If there was a cut here, then this will start kind of seeping out of the cylinder, right? So if you have a finite solenoid, then this will be like this, right? Something like this. It's like a magnet. Is it? Or flows out, kind of. Right. Okay, so what's the expression? Says mu naught has to be there. Let's say this is each of this has a current I in it. It depends on proportional to current. And what else does it depend on? Is it dimensionally correct? What's the dimension of magnetic field? What's the unit of magnetic field? Maybe I should say that. What's the unit of magnetic field? Tesla, right? It's also measured in Gauss, but in SI units, it has to be Tesla. Right. So the magnetic field is measured in Tesla, and 1 Gauss, it's like we work with meters, but then certain units are very common, like mile is very common, but so we need to know the connection. So similarly, Earth's magnetic field is 1 Gauss on the surface of Earth approximately. That's equal to about 10⁻⁻⁴ Tesla. So always in Tesla, if you're working in SI units, which we have been consistently working on, Tesla is the important unit and not Gauss. So since we know the magnetic field due to a wire, we know what we expect. That is, for a wire, it is mu naught I over distance, right? So there has to be a distance, right? Just to match the dimensions, right? What distance is that? Right. We already argued, or we didn't argue. We said that this is constant, like inside a solenoid, it's a constant. We didn't argue anything. It's so. What about the units? Like, what else can come there? What's the expression for magnetic field due to solenoid? What's the formula?
Well, there's a number of loops.
Yeah. It's a number of loops. Okay, number of loops. So is that right?
And then the length of the solenoid then?
But length I said is infinite.
Okay, yeah.
Maybe, yeah, you're thinking correct. Is that right? Number of loops. Dimensionally it's wrong.
Well, there's the circumference. That's it.
Circumference is radius. We said it's
Which we said we
independent
could-
of radius. Something is outright wrong there. I mean, I'm tricking you guys. So.
There was something about the loops per unit length.
Yeah, loops per unit. So this is not n. So I think you were almost there. So this is n over L, but L is large. So you don't say it is capital N, or if I say it has to be defined there. So n is equal to number per unit length, number of loops. Loops, right? Is that loops? Yeah. Number of turns, I mean, number of turns per unit length. And that gets the dimension right? So, because actually number of turns is not meaningful in an infinite wire because it will always be infinity, how much ever you keep. Always. So infinity over the length, which is also infinity, that can be finite, and that's good. So that's your magnetic field expression inside the solenoid or outside the solenoid. What is the magnetic field outside? So this is inside. This is all review, right? But we want to derive that. What about the magnetic field outside the solenoid?
There's no magnetic field outside.
And why is that?
Just remember that there's no magnetic field outside, but there is a magnetic potential. That's what
Yeah, that's correct, actually. That's a very correct answer. Very good. But we don't know why. So these are our results, right? We want to derive this all using Ampere's law, right? So the answer of the magnetic field for Z hat mu naught I n inside, and it is 0 outside. Good. So, and importantly, I think Jordan said it very rightly that we're not talking about potential here, magnetic potential. In fact, magnetic potential can be there outside very, it has consequences. Remember, one would argue that, oh, so what, magnetic vector potential is there outside, but that's not a measurable quantity, right? It's a gauge dependent quantity, who cares, right? But we argued last time that the loop integral of that has a finite meaning. So if we can do an experiment which depends on this total loop there, then you can get some consequence. Even though there is no magnetic field outside, you can have an effect due to the magnetic field just because of this gauge quantity which has the loop integral of that. And there are quantum effects related to that, very counterintuitive. But you can get, that's a very good point. But we want to do a simple case here. Let's not even worry about this radius. Let's get this from Ampere's law. If that is really true, Ampere's law should be able to tell that, at least to a certain extent, we should be able to argue that. So let's see how do you go about that. Notice this is infinite, so let me stretch this out so that I can draw some loops here. So how do we know that it is constant to begin with? So let me have a loop here, like an arbitrary loop here. So that's inside. So the loop is completely inside my inside the rectangular loop, completely on this plane, let us say, and it is inside that cylinder. Let's say this is radius, so there is a radial distance, right? So this is at a radial distance 1, that's a radial distance 2. Like, is that readable online? It's radial distance 1, radial distance 2. Okay. So Ampere's law, we don't know that it is constant yet, even though we declared that it is constant. So do the loop integral. So this is dl dotted with b has to be equal to what is the enclosed current inside this loop? Right hand side?
0.
0, right? I said it's inside the cylinder, so that's 0, right? And symmetry, by symmetry argument, you already say that it has to be in the z direction. Okay, so dl, the magnetic field is assumed to be by symmetry argument in the z direction. How can you argue that? Because for a single wire, we know that it has to be a looping, so that this loop will catch up with this loop and catch up with that loop. So you can argue that this is, if for an infinite wire, this will be actually has to be in the z direction, plus or minus. So dl dotted with bz, the horizontal lengths do not contribute because of the dot product. So this is b of rho now. Right? So it can depend only on the rho from.
I have a quick
Yes,
question.
yes.
When you write the contour integral there, I thought that would have to be like on the contour of the surface itself. I guess that's why I'm a little confused.
Contour of the surface or the boundary of the Amperian loop. So the loop surface I'm talking about is this. It has nothing to do with the surface of the cylinder.
Okay, okay.
Right? It is an arbitrary abstract surface, any surface for that matter. Right? And that's what I will do here. I will take 3 surfaces. It doesn't have to be the surface of the cylinder. I'll take any surface I want. So I'll do this for 3 surfaces and get 3 results here together, which will convey that. Okay. So here there are only 2 of these lines contribute. On the, so let's say this is of length L, so it is L times B of rho 1, and 1 is going in the opposite direction, right? So there is a negative sign that comes in due to that. So minus L times B of rho 2 has to be equal to 0. This immediately tells that this is radius dependence inside the position independent inside. So this implies that B of rho 1 has to be equal to B of rho 2. Right. So it is independent of rho. Already we argued symmetry wise that phi, it is phi independent, z independent. So that implies that this is constant. Right. So already we have one part of the solution. And then let's say, now let's change the loop. Let's take the loop to be partly inside and partly outside. And the argument is the same. So this is B of L times B of rho inside, rho 1, let's say, or let's say rho less, right? That means it's inside. So rho less minus L times B rho greater has to be equal to, this time, the current is not 0, right? The enclosed current is not 0. How much is the enclosed current? We said it is number of turns per unit length. The length we know is L. So number of turns per unit length, that's the total number of turns. So it is, so let me say this is, how do I get this? This is, let's say, mu naught times I times total number. So this is the total turns in L. So this is total in L. So then I divide by L and I get the mu naught I. So this seems to suggest that B less, I still in the, yeah, B less is equal to B greater plus mu naught I times N. So that's all, that's the expected result, but we have to now show that this is actually 0. the magnetic field outside is 0. Question, Rob? No?
Doesn't the n become lowercase?
Oh, yes. Thank you. N is equal to n over L. Like number inside that loop divided by the length L. But for the whole wire, the total number of loops is large. Yeah, thank you. So now we have to show that that's equal to actually the p greater than 0. So now we do the same thing for outside. Again, there is row 1 and row 2, let's say. This is row 1 and row 2. This time both 1 and 2 are outside. Again, there is no enclosed charge in there. So no enclosed charge in there. So I'll say L times B of row 1 minus of L of B of row 2 is equal to 0. So the best I can get out of this is that whatever is the magnetic field outside has to be a constant. Right? If it is independent of rho, it has to be a constant. But then you require that the magnetic field is 0 all the way at infinity, right? At the radial infinity. So let B of rho be equal to 0 at rho tends to infinity. So that's, if you require that to be 0, then you can conclude one more thing, that this is actually 0, and that gives you your result for a solenoid.
So the
Yes.
the X and Y components of the magnetic field don't contribute, but then the Z component does, but it's equal to 0. Like if you were to do,
Tell that again.
like the magnetic field in the X and Y directions are 0, like they don't contribute, but then
Yes, that we used symmetry arguments to say that. That's not, Ampere's law is not saying that. We said if you have a cylinder and you have a vector field associated with it, it's the same argument that I was talking about here, right? Why can't we have such a geometry, right? To begin with, we say that if you have an axial geometry, the magnetic and the current is all in a plane, like current here is in a plane, right? Then the magnetic field has to be perpendicular to that. So that's the beginning point, that we are saying that it has only Z direction, right? That's a symmetry argument. You have to use other physics to motivate that. From that point on, you can derive all these things. Is that your question?
yeah, I was just thinking, like, I guess in a slightly different way, if you did partial by partial X of the magnetic vector potential, and then minus partial by partial Y of the.
Yeah, the argument is that if you, like, there is cylindrical symmetry here, you cannot have so whatever is the physics here should be the same as here, right? So it has to be phi independent. So you would say there is no angular dependence in here. So that's your phi, let's say. There is no angular dependence in the magnitude of the magnetic field. There is a direction also associated with that. So that's a harder thing to catch, but magnitude-wise, it cannot depend on the angle. It cannot depend on Z either, because whether you're up here or there, it shouldn't matter because that is because of symmetry. And direction-wise, then you have to use the other part of it, and that the current is conserved. That's also, so two of those equations here are used. Did that completely answer, or maybe at least partially answer your question?
Yeah. Yeah, I understand what you're doing. I understand. I got you.
There is one more nice feature in this, which is counterintuitive. And here is the following question. So we have shown that for a solenoid, so let me show the solenoid in the following form. So that's my solenoid, right? So let's say this is I. And by this I mean there is a coil, right? So this is a solenoid. The understanding is that there is a hole along the z direction, so this is z direction. Like this is repeated in the z direction, and that's okay. And the magnetic field is all like this. And we also said this is radius independent. That's okay, that's good. Okay. But what about, how does it depend on this geometry? In the sense, is it necessary that this should be a circle? So the question is, so if I have a solenoid of this kind, I can change my geometry. So still there is a current I and it is stacked. It's a coil of current, but the cross-sectional area is no more a circle. Cross-sectional area is no more a circle. And the claim is still B is equal to Z hat times mu naught I times N inside and 0 outside. Check. Or an exercise could be a quiz, right? Like I cannot give this as a homework because I myself have not done it, but I sometimes give it just for motivation. Think about, is it possible, like based on the arguments we did, is it possible to do this for a general example? So just for your thought process, right? If you can derive it, that's good. I suspect you cannot do this for solenoid because you cannot use the symmetry. You cannot use Ampere's law because of symmetry arguments will fail there, but then you have to go to the scratch and get it done. So go and derive solenoid equation from the scratch. It's not very hard, but then you have to do this also. There are articles written about this. Look it up. There are standard articles available. Yeah, I don't remember it out of my head. Look up American Journal of Physics, if you get interested. So that's just some information for you. Okay. So that's the only two examples. So there is torus, and you can think of a flat sheet of wire. So there are a couple of more classic examples, but I assume you have seen that here. That I don't have anything great to add on to that. Okay. Any comments or questions as such? Okay, so let's do circular wire. At least do simple couple of things that we always do in undergraduate physics. So circular wire. Let's at least calculate the magnetic field. So let's say there is, so this is a circular wire, and that's the center of the wire. Let's say there is a radius r associated with the circle, that's radius. Or maybe A, right? Doesn't matter, capital R. Okay. And for the moment, we have about 20 minutes. Let's concentrate on the magnetic field. We'll come back to magnetic vector potential, right? Remember our magnetic field formula at observation point, right? At point R, the magnetic field is got using, can be derived using Biot law, right here. 4 pi d cube r prime. And what is the formula? You guys have done homework? Check it, right? J at r prime, right? This is at the source crossed with
R minus R prime over R minus R prime magnitude cubed.
good. So that's not mag and this is cube. Very good. So where is the source here? This is all on this wire, right? So it's only on, so R prime survives. So this is R prime. So if that is my center, so that's my R prime, let's say. If that is my origin, that's my R prime. Where is my R? Right? R could be anywhere. Right? So in general, R could be anywhere, any observation point, right? Inside, outside, anywhere. So that's my R. In general, I would like to calculate the magnetic field at any point. What about the current density? J of R prime is equal to, there is a current I going through this. What's the direction to begin with for J? Let's say there is a current going through this. So it is phi hat, right? So the direction is phi hat. Current is I, but current times area, right? So there has to be, sorry, current divided by area. So there is a delta function in there. Now, what is that delta function? So it is an area, remember, of area of what? That's the area of this wire. Right. So that's what we have to capture using the delta function. What is this plane here? So that's the plane we are talking about. But it has to be, what will that be? Let's see. First of all, there is surely a delta function at rho minus a. Right? But what is the other delta function? Like, is it z or is it phi?
I guess it depends on where R is, right? If R is on Z, then it's Z. But if it's anywhere else, it has some sort of phi dependence. I just don't remember what the delta function.
Yeah. So suppose I were to take this small element here. So there's this tiny element, right? What's the height of that? So let's take this as a cross section, right? What's the, so maybe, yeah, I think I can do this better this way, right? So this is the, probably maybe like this. Does that make sense? Oh, is that in the view? Right. And now, what's the cross section we're talking about? That's the cross section we're talking about. And First of all, this is dz. This is rho d5. Correct. So this length is rho d5. This is rho dz. And what is this? This length. What is this length?
D rho.
D rho. Correct. Correct. So if we want to specify this now, so this is our this is the area, right? That is my area. Yeah, so there is a dz there. So my area is dz times d rho. So if I want to specify this, so I will have to specify my z and specify my rho. So I already specified rho, so it is not the angle that comes in, it is z. It is delta of z. Where do I keep my circle? So it is in some plane at some height. I can choose this to be 0. We can also keep this, let's keep this to be 0. Later on we'll come and, actually for circle, it is easy to keep it at 0. But if you want to do a solenoid by any chance, so once you get the circle, if you stack the circles all over together, you can actually do the solenoid. Solenoid is nothing but stacking the circle. So then you want to keep the z prime there so that you can track that for the next step. But let's keep it at 0. And this all has to be primes. Okay, so that's the argument. And let's see what it is. Now, in general, it turns out that this is hard to do. Okay, and we'll go and later on do this. So let's make a very simple approximation. An important point on a circle is at the center. Right? So let's say, what's the magnetic field at r equal to 0? Let's set r equal to 0. It's a very special point. And that clearly simplifies a lot of things. And this is not an integral parameter, right? That's an external observation point. I can set that to 0. Right? So, so that works. So B at 0, right, at the origin. Yeah. Yeah. That's equal to, there's a minus sign that will come out, mu naught over 4 pi dq r prime, j of r prime, crossed with r prime over r prime cube. Correct? What is r prime cube? R prime is nothing but a, right? Magnitude of r prime is just a, and this is rho hat, right? So I can do certain things here immediately. That's minus mu naught over 4 pi, right? 1 over a cube, because that's what it is. R prime is actually a times rho hat. Rho, right? Rho prime. Right. Is that right? No. A times rho hat, right? If I pull out the dimension, then it's a rho. Right. So that's a square. That's a square times d cube r prime, which is having x, y, z, right? So let me put it in cylindrical coordinates. So this is dz prime. Minus infinity to plus infinity. I'm pretending that sources could be anywhere. This is 0 to infinity, rho prime, d rho prime, 0 to 2 pi, d phi prime. Right? That's the volume element for a cylinder. J, we said, is, oh, this is, by the way, when I wrote the magnetic, a small point here, I said rho prime here, this also should be prime. Right? So there are two phi hats actually. There is an observation phi hat and there is a source phi hat, and they could be different. Right? This is a prime phi hat, right? Because phi hat can change with integral. Right? So that's a position dependent quantity, so that can change, so one has to be careful. Coming back. Okay, so this is I. I can come out. And there is a phi prime, so this is, let me write this rho prime minus a rho of z prime. And there is a phi prime hat crossed with a rho prime hat. And that's it, I guess, correct? I collected everything, I suppose. Okay. What is phi prime minus crossed with rho prime? Phi hat crossed with rho hat?
Minus C.
Can you move
Minus.
the camera just slightly?
Oh. What did you want?
Just to move the camera. Oh, never mind. I guess my Zoom meeting was actually off the screen. That's
Okay. Okay. So I was asking, what is the cross of this? So Moses says this is z hat prime, but that z hat is prime and unprime are the same quantities because z hat doesn't depend on position. So that minus sign cancels out. So that's a lot of simplicity now. So that's equal to minus and minus gone. So that's z hat mu naught over 4 pi. And as I over a square. And now I can do the z prime integral and rho prime integral. Z prime integral gives me nothing. Rho prime integral gives me an a. Right. And I am left out with just a angular integral. That's it. It's trivial, which is 2 pi. So that's equal to z hat mu naught over 4 pi I over a times 2 pi. Which is indeed the expression for a magnetic field only at the center of the circle. It doesn't work everywhere. So this is typically written as mu naught I over 2a, right? Since we always work, if you're working in SI units, that's the expression. But if you're working in Gaussian units, then this 2 pi I over a will show. Only true only at the center of the circle. But then you might think, oh, can I do something better with this? You can also get it everywhere on the axis. You cannot get it away from the axis. You can at least get it on the axis. We'll come and do that next time. But one thing we can try, okay, so that was very easy, right? It didn't take too much effort at all to do this. Can we do the vector potential at the center, right? Why not try that? Like, can we do vector potential at the center of the circle, right? So let's attempt on that, and we'll see. Or let's remember your expression for so since it went so smoothly, let's try vector potential for a circle. So that's mu naught over 4 pi. And what's our expression for the vector potential? So no cross product, just J. Right? J of R prime minus R prime. That's it, right? There's no Q. This is 1 over R. Yeah. Again, we are interested only at the 0, right? Only at the right at the origin, so that's 0, right? Right at the center of the circle. I set that to 0, so that's mu naught over 4 pi d cube r prime, and this is j of r prime over r prime, which is a, right? Magnitude of r prime, that's just a. Let's do that. So that's mu naught over 4 pi 1 over a. This is minus infinity to plus infinity dz prime 0 to infinity rho prime d rho, right? And what else? Right. Help you one more, right? Yeah. Z 0 to 2 pi d rho prime. Seeing what I'm expecting. Okay. Oh yeah. Yes. Okay. So this is remember 5 prime here, and then I times the 2 delta functions. Let me go vertical space. So this is rho prime minus a e prime. Sorry about that. That should be clear. Yeah, hopefully. Okay. But I can do the z prime and rho prime. U naught over 4 pi 1 over a. Z prime gives you nothing. Rho prime gives you an a. And because there's a rho prime there. And what you left out with this 0 to 2 pi d phi prime of phi prime. Correct? And a's cancel out. Right? And what is that equal to? What is that integral equal to? So one more step I correct. Mu naught over 4 pi, a's cancel out. Oh, there was an I, right? I missed somewhere. Huh? Oh, is the I go? Yeah, I. The dimension I was worried. Yeah. Okay. What is that equal to? So remember, this is a circle, right? The unit vectors, phi prime is here, right? Tangent. And remember, these are vectors, so I have to add all the vectors. Like these are all unit vectors, lots of unit vectors, all over on that circle. Add up all those vectorially. What do you get? 0, right? Because they're vectors, right? For every vector on the top, there is a diametrically opposite canceling that, right? So the vector sum is equal to 0. Right? So the magnetic vector potential at the center of the wire is equal to 0 up to a gauge, right? We already argued that this is off by a gauge, so that's not really meaningful in that. But one could argue, or one could get confused, or there is a argument one can make that, okay, A is 0, so magnetic field is curl of A. So in some gauge, B is 0. Like in a particular gauge that we chose, right? A is 0. A is 0, B is 0. Right? But magnetic field is not gauge dependent. Right? Magnetic field cannot depend on. So I'm tricking you guys. So what's wrong in the argument that A is equal to 0, so B is equal to 0? I think I'm tricking you guys.
So, yeah.
Yeah.
Well, A could have components that cancel when you take the cross product. Or,
Something more? Yeah, something. No, not because of the vector nature. Something else? So, for example, let's say, suppose acceleration, right, is dv by dt. If v is equal to 0, acceleration is equal to 0. Rolf says no. It's a big no, he says. Why not? What's wrong with that? Velocity is 0. Acceleration.
Could be a turnaround point.
Yeah, turnaround point, right? It could be a turnaround point that you throw a ball up in the air, right on the top, it is 0, but right adjacent to that, because derivative involves 2 points, right? It's 1 point and another point. You can go as close to it as possible, and you have a non-zero point there, and it's a change in A that is important. Same thing here, it's a curl, yes, vector nature, but it's a change in A that is important. It is 0 at the center, but right next to that point, it could be, or it has to be something else, because B we said is non-zero. So just A being 0 doesn't imply that B is equal to 0. So we couldn't, we did get A, but that's not very useful in a sense, or it doesn't help you calculate your magnetic field. Potential should help you calculate your magnetic field. In that sense, it is not very useful. But yeah, A is 0 in the Lorentz gauge. In the Lorentz gauge, A is 0. Yeah, good information, but we cannot extract magnetic field out of it. Exactly like if you're given that right on top of the trajectory velocity 0, so what is the acceleration due to gravity? We cannot get that information from 1 point. Good. Yeah, so let's stop there, and we'll come back and do more on circular wire next time. Okay. Thank you.
Any game I want to play. I got you.
It is easier to shush teenagers whenever you're trying to have a Zoom meeting.
It is easier to.
It's easier to shush teenagers. It's still necessary, just like it is with toddlers and younger kids. They're old enough to recognize.
Yeah. I got it. Yeah, but they were quiet, or maybe Alia was muted, right? Were they quiet all the time, Alia, or it's just that I stopped and then I heard voices?
Oh, it's so noisy.
No, she was.
With the Shari, her daughter is in and about, and
She's always running around, and
of course, my wife, who wants more grandkids, is all giddy about it. She's like, "No, let her play on the camera."
yeah. Nice. Yeah.
My stepdaughter has a tendency to walk into a room, just whatever she has been saying on her way from the kitchen or whatever, she has to say it. And sometimes both of us are on a meeting.
Got it, yeah.
Not you.
No, I understand, like, I'm sure there has been, I mean, not necessarily the people around, that could be embarrassing situations with all this. Yeah, so. Well, this is the new norm, kind of.
One of our staff members, her two younger kids would come in behind the camera, so their mom didn't know what they were doing, and they'd be like, they make faces, and everybody started laughing.
Yeah. We had a similar situation in one of our colloquiums. Bamsu's daughter was trying to come, and Bamsu was very nice about it. He was trying to very nicely, like, he doesn't want her in there, but at the same time, he's not showing her off either. So he was trying to very politely manage whatever was going on. So I'm sure it happens. Yeah.
I've had people that had to bring kids into class, and we're not supposed to, but
Yeah.
my stance is,
Good.
I actually keep pencils and paper and stuff to help keep them occupied, because I had to bring my daughter to class
Got it, yeah.
when I had no other, it was either cancel class or she sits in the back and draws and colors, because I may have only had one class that day or something.
Wow. So is there really a rule saying that you cannot bring, like, written rules, you're saying?
There is a written rule, but
Yeah, no, that's, I'm for it.
if my dean is a really good person, because he was a faculty member, he was the same way.
Yeah.
His official stance is don't, but when no one else is looking, he's
Yeah.
like, don't worry about it.
Yeah. I mean, it should be case to case. Yeah.
I'll never forget in my calculus 3 class. My professor was like a very mathy guy. Just everything he sees is just math. He can't communicate well with people outside of that, but he loves his grandkids. And there was a snow day where the small schools around the area would cancel, but the university wouldn't cancel because they were prepared for snow and stuff like that. So he brought his grandson to class, who was probably 6 or 7, and he wouldn't discipline the kid during the class. So he was like trying to teach us calculus on the board, and he was writing, and while he's writing, his grandson is erasing parts of the board and then drawing just like the things that he could draw, like smiley faces or the letter A, So, and the professor never said anything like, hey, maybe you should sit down in the back, because he's just thinking math and never looks back at his notes. He's just on the board. And just everyone sitting out in the audience just kind of chuckling to themselves like, we're not getting much out of this lecture, are we?
You are if you write fast.
Yeah.
Well, the professor couldn't see us anyways. He has like these really, really thick glasses. And but it's like they didn't work, because he would take a piece of paper like this, and his notes, he would just tear off a corner like this, and his entire class notes would be on this little corner. And he has horrible eyesight. So like every time he wanted to look at his notes, he'd like have to do this with his glasses like 100 times looking at the note, And so he probably knew none of us in the class, because I doubt he could see any of us, but he was an interesting guy, to say the least.
Yeah, obviously a memorable class.
Yeah.
Interesting. Yeah.
Like he wrote this big paper, and there was no solution for it for a long time, about what is the optimal way to cut a pizza. Is it odd slices or even slices, and what guarantees that you get the most pizza, like that you actually get to consume the most pizza, if you cut an odd number of slices or an even number. And this went unsolved for like 15 years, and I guess a couple of years back they actually found the solution.
The solution, I see.
I don't remember what it was, but there's a whole paper on it.
So do you cut it in even or odd? Is that the question?
I don't remember, but there is out on the web. You can search for it and it'll tell you.
Okay, nice. Okay, cool. Okay. Shall we call it a day? Day or what is it? A class?
See you guys on Tuesday.
Yeah.
See ya.
All right,
Yeah.
see ya.
Enjoy.
See you guys.
Okay, bye.